Okay, good afternoon. This is work that has been done by myself and my grad students, Ian, Dan, and Matt, and then Mackenzie Skiles, who just finished up at UCLA and is now at Jet Propulsion Laboratory, has also contributed to this. And so we've all seen this work presented already today, which is basically, we know that our glaciers are retreating. We've got the classic picture of South Cascade Glacier up there on the top left, and the glacier mass balance record on the bottom, and then Moat's paper from 2005 that we've now seen several times in this session. Is there there isn't one? Okay. And so when we discuss these changes that are happening in the snowpack, what is most commonly referred to is, of course, the changes in temperature, and we look at changes in precipitation. But there's another factor that hasn't been considered as much, at least in this region, and this is the deposition of light-absorbing impurities. And by light-absorbing impurities, I'm referring to black carbon and dust. And so black carbon is produced by the incomplete combustion of fossil or biofuels. And so I've got pictures down here. We can talk about anything from cars, ship traffic, industry. Here we have a forest fire. And those have gotten a lot of attention, particularly in the last decade, because black carbon is now recognized as being second only to CO2 in the positive climate forcing that is occurring. And then the other aspect of this is dust. And if we want to look at this regionally, dust is coming from both natural sources, and then with a lot of land use changes that have occurred, we're getting increases in dust emissions. And so my concern with both of these things, black carbon and dust predominantly, but organic material and things like volcanic ash are also considered light-absorbing impurities, is that when these are deposited upon the seasonal snowpack or onto glaciers, they cause a darkening. And this is a figure that demonstrates this very well. This was taken by my student Matt Jenkins, and he had gone out for a hike one morning, and this is where you see his footprints. And when he had walked across the snowpack, that had removed the surface snow that had impurities upon it, and when they came back from their hike, you can see the difference in the amount of melt that had occurred just during one day from the difference of where you have impurities deposited and where there aren't impurities deposited. And so this just really demonstrates the efficiency with which these light-absorbing impurities can contribute to melt. And so Hansen and Nazarenko, in an important paper that was published in 2004, there's this quote from that we suggest that soot contributes to near worldwide melting of ice that is usually attributed solely to global warming. And so it was this paper for me that really gained my interest in black carbon and has kind of directed my career since then. So this is what we know about how black carbon has varied in the past. For the most part, we've got a good grasp on fossil fuel emissions historically, and we're able to do that based on inventories of fossil fuel use. And so this is there's a few different inventories out there, but this is one from Novikov in 2003 that shows that globally black carbon has increased a great deal over the 20th century. And then we can look at black carbon emission strength over there on the right. And I've got the Pacific Northwest blocked off there in red. And what you can see is that there's certain hotspots of black carbon emissions. So Asia, of course, is a big one, and that's where the majority of my work on this topic takes place, usually in the Himalayas and the Tibetan Plateau. But there's reasons for focusing on this problem also in the Pacific Northwest, and I'll run you through those. So first of all, if we're looking at where we've got glaciers in the continental US, the Pacific Northwest is, of course, the hot spot. The snowpack and the glaciers are warm. We've already seen this, that this region has a warmer snowpack, so it's more sensitive to small amounts of energy being added to the snowpack than a colder, more continental snowpack. And then because our mountain ranges here are relatively low elevation, they're also closer to emission sources. And then the last thing, because my background largely has taken place studying this problem more in the Himalayas and in eastern China over there, we've got very large emission sources. I was interested also in the potential for trans-Pacific transport of the black carbon to be potentially impacting the snowpack here. So that was one of the ideas I originally approached this to investigate in this region. So what do we actually know about this at this point in time? Not a lot. There was a modeling paper that came out in 2009 that modeled the black carbon deposition, and we can see that we have some hot spots around Seattle and Portland. And then Chin had modeled the changes in the spring snowpack due to the black carbon deposition, and was showing that that there was a decrease in the snowpack because of black carbon deposition based on his model results. But one of the challenges that we've had is that we have very few observations to actually constrain this. There were a few measurements, just point measurements that were made in the 1980s and a couple in the 1990s, and it's largely been abandoned since then. And so that's been the focus of my work in the region over the last 5 years. And so we've been making measurements of black carbon and dust on glaciers and in the seasonal snowpack in the region. We've been working with the National Park Service, so with John Riddell's group, on the glaciers that they monitor, and then we've got a seasonal site that we've been monitoring for 4 years at Blewett Pass. So I'll just run you through some of the findings that we've had. So I'll show you the seasonal variations that we see in black carbon deposition. I'll touch on the role of forest fire, and then I'll show you some results that we have from recent work that's looking at 20th century black carbon deposition from an ice core drilled on, from South Cascade Glacier. So we've monitored the snowpack continuously over 4 winters, and so what you're seeing in these graphs here is the red line is the snow water equivalent, and then the black, let's see here, the black solid line is the one that we want to focus on, which is black carbon concentrations in the snowpack. And what those show is that the black carbon concentrations tend to increase into the springtime. And so one of the major causes for this is that that's when atmospheric black carbon concentrations are also increasing. And so what's interesting about this is that when we're starting to lose our snowpack is also when we're getting the most black carbon added to the snowpack. There's another cause for this, which is not only do we have higher black carbon concentrations in the atmosphere, but we've also been able to document that as the snowpack melts, the black carbon tends to get trapped in the snowpack and concentrations increase. So black carbon, it's really dark and absorptive, and so this is just something that's reducing the albedo of the snowpack and allowing more energy to be absorbed and contributing to greater melt. So the work, I've got the map down here on the bottom left where we had, or your bottom right, where we had been monitoring black carbon on the glaciers. And the initial idea behind our sampling was that we wanted to look at the spatial distribution of black carbon in the state. The logistics of getting in and making the measurements on the glaciers are fairly involved. And what we found when we started to actually look at our data is that rather than capturing the spatial trends that we had originally hoped to capture, we were more so looking at a seasonal trend. And so what I'm showing here is over the course of 2012, this was all work that Ian Delaney had done in collaboration largely with Mike Larrabee, is that we saw that there was a real increase in black carbon concentrations on the glaciers also as we continue into the summer. And the reason for this is that during the summer, we've got very little precipitation falling, and then we've got much higher atmospheric concentrations of black carbon that we see here on your bottom left. And combined with the melt that's occurring on the glaciers, we are basically seeing that these light-absorbing impurities are really increasing their effects later into the summer. Okay. So one thing that was interesting that happened is that we had been monitoring the snowpack up at Blewett Pass for 3 winters, the 2010, 11, and 12 winters. And then at this time in 2012, we experienced a large forest fire, the Table Mountain Fire. And so if any of you happen to be on the east side of the Cascades during that point in time, I'm living in Ellensburg, and the air quality was absolutely horrendous at that point in time. It was up to hazardous levels at some points in time. And so this provided us, though, a very interesting opportunity, which was that we were left with this very large burned area, and we saw changes in the amount of black carbon that was in the snowpack in 2013. So we ended up having quite elevated concentrations relative to the 3 prior years. And so this is showing on the top left here is showing a picture of a forest fire that was the Snag Canyon fire that burned this summer. And then on the top right over there is showing what these areas look like post-wildfire. So this is in the following winter, and what we're left with is just these burned trees that are just covered with char and are an excellent source of black carbon to be deposited on the snowpack. And so that's what we saw oops, let's see, if I go back here, this is what we started to capture. Our study site is actually outside of that burn area, but just due to its proximity to the Table Mountain burn area, we were able to see an increase in black carbon concentrations. And so this is let's see, I need a pointer. So this is Blewett Pass. You can see the road going up there. That's highlighting where I've got Blewett Pass there is showing where the Table Mountain burn area was. So right here. That also up there on the right. And then the Snag Canyon fire has intersected it this year. And so this provides us an interesting opportunity to see how long these post-wildfire effects end up affecting the snowpack. So we're left with those charred materials, and one of the questions I'm interested in trying to answer is, well, how long through time do we continue to have black carbon that's getting integrated into the snowpack? And so what we were able to do in 2013 was we compared both in the burn area and outside of the burn area how much black carbon was getting integrated into the snowpack. And it turned out that it was a quite bit higher amounts. So we've got the red being in the burn area, the blue being outside of the burn area, and then the green and the black being pre-forest fire. So that's something that we're going to continue to look at in more detail. Another aspect of the work that we've been doing has been looking at black carbon from ice cores that we've been collecting from the glaciers in this region. And so we went to Snow Dome in 2012, which is out flowing off of Mount Olympus. And my original motivation in going to look at Snow Dome was thinking that since it was upwind of the Puget Sound area, that this would kind of give us a background of black carbon concentrations in the area. Let's see, I'm running low on time here. But basically on the right, the upper right image there, what you can see is that we've got layers in the snow in the side of the glacier where you can see those light absorbing impurities. These are some pictures of where we drilled the ice core. And then this is the black carbon and the dust records from those. And what this shows is that basically in the 2011 summer, you can see the piece of ice that we retrieved down there on the bottom right, is that we had a magnitude higher concentrations than what we measured in the 2012 summer. These are really, really high black carbon concentrations, 3,000 micrograms per liter, which is about as high as anything I've ever measured in areas that have much, much higher concentrations. And so what we came to realize is that these were caused by the Big Hump wildfire that had burned in the region. If I had a pointer, I would show you on the map where that fire area was. Because I'm running low on time here, and this has got so much data on this, I won't be able to run you through it in too much detail, but what we have on the top here is showing wind direction, and what we saw, if you can see this gray band right here, what we were able to document is that there was a change in wind direction that caused emissions from Big Hump to be deposited on the glacier. The middle panel there is atmospheric elemental carbon from the area, and we see elevated elemental carbon at that same point in time when we know the winds shifted to move black carbon to the glacier. And then we were able to look at changes in discharge. The first 2 weeks of September that year were dry. And so we had a really nice experiment where we could say, okay, we know within a day or two period when that black carbon fell onto Snow Dome, and then we were able to look at the temperature and the discharge data from there, and we were able to show that there was a doubling in the discharge that happened as a result of that black carbon deposition. And we've also been able to identify charcoal in there, and then Bill Bacchus had been doing some aerial flights over the area, and so we know that the black carbon had impacted that. Let's see, am I out of time? Okay, I just want to show you guys one last thing here, which is that there was an ice core that the USGS drilled in 1994, and so we've also been working on that record. And so this is a picture just showing that we can look at the dust and the black carbon records from that ice core. We're still working on the dating of this, but we now have a record of how black carbon concentrations deposited on the North Cascades have varied over the 20th century. So the gray area there is showing 1963. And this looks very much like what we think the emissions looked like based on the fossil fuel inventories. But what I have circled there with the circle is highlighting that we have these high outliers that we think are from fire. So we're still working on that. And I know I'm running out of time here. So basically where we're at right now is we know that black carbon deposition, it's happening at certain times in high enough concentrations to be contributing to melt. It's going to be high elevation snowpacks that are going to be most affected. And the highest concentrations that we observe in the region are from forest fires, particularly on glaciers when we have forest fires coincident with snowpack on the ground. So we need to do more work to actually look at the efficacy of black carbon versus dust deposition on the glaciers, because oftentimes we have much higher concentrations of dust than black carbon. And then just the last things is just what are the relevance of this in the changing climate in the Pacific Northwest, which is that we're going to have more snow to rain, and that's going to mean a smaller snowpack, more glacier retreat, and those black carbon concentrations are going to get more concentrated in the snowpack, so lower albedo. And then the last thing is we know we're facing an increase in forest fires, so this concern we have about the fire deposition is also going to increase. So yeah, sorry for running over. Is there?
We've got time for a couple questions. While we're looking for a question, I'll make a comment. That Table Mountain fire she talks about, I live right over the hill from her, and for 7 straight weeks, which started yesterday, 2 years ago, our air quality ratings were 3 to 4 times worse than Beijing, China. It's a lot of material. Any questions?
You mentioned that atmospheric black carbon concentrations tend to increase in the spring. Why is that?
It's both the, it's largely because of that it's drier, and so you don't have it being scavenged out of the atmosphere, so the precipitation isn't removing it. And then I also think that you get the planetary boundary layer tends to become elevated, so for the higher elevation sites, more of that pollution is also getting lofted up higher. In terms of it being a change in actual emissions, I don't know that plays so much of a role.
Hi. You mentioned that. Oh, sorry. Oops. Sorry. Did I go? Okay. You mentioned that the black carbon accumulates in the snow after as it's melting. So what happens with after that? Does it just keep accumulating, or does it go somewhere with the snow melt? The study up at Blewett Pass was largely to look at black carbon processes in the snowpack because those haven't been really well understood. So it depends kind of on how quickly the melt happens. So if you have really, really rapid melt, then you can flush the black carbon out of the snowpack. But if you have slower melt, then we see that it actually ends up getting more trapped. Once the snow is all gone, then it's, some of it's integrated into the soil, some of it is just discharged into the streams. But the concentrations in streams tend to be quite low.
Question was about the modeling slide about early on, maybe a third of the way through the talk. And I noticed in the Pacific Northwest, it was the slide that showed the reduction in snowpack.
Right.
There you go. So Idaho and western Montana, why is there so much blue? I should be able to tell you that. Some of as you move more continental is they also have a smaller snowpack. So this is something I would be interested in working on in that area. So with a smaller snowpack, you're going to tend to end up with higher concentrations, whereas where you have a big snowpack like you have around here, it tends to get more diluted. One of the reasons, though, that this area becomes so interesting is because we are so close to that melting point, and so just the added energy from the black carbon can also have a big role here. Mm-hmm.